Now I'd like to introduce Srikanth Sundaresan, who is here and going to talk about some measurement studies that he's done. Hey. And there's a clicker here. And this is related in a way, so there's forward, back. Forward. No, forward is this big deal. Okay.
Cool. Morning. Thanks for having me over at NANOG to talk about my research. So I'm going to talk about a recent work on trying to understand bottlenecks, throughput bottlenecks in the last mile. So specifically, we ask whether it's possible to identify throughput bottlenecks to either your access link or your wireless network. So I'm Srikanth Sundaresan. I'm a postdoctoral researcher at the International Computer Science Institute across the Bay in Berkeley. And this is joint work with Nick Feemster at Princeton and Renata Teixeira at INRIA. So I'm sure most of us here in this room have grappled with the home network at some point, trying to figure out why a video stalled or your VoIP call halted, and struggle to figure out why that happened. So one of the reasons why it's so difficult to understand is that, well, there are many sources of problems. In the last mile, you could have congestion in your ISP, you could have wireless issues, you could have end client issues, poor OS or bad hardware, or even beyond the last mile, you could have peering issues in your ISP between ISPs, and also server-side issues, poorly designed application, whatnot. We focus on the last mile in this work, and we ask, so how can we determine whether there is a bottleneck in the last mile? And if there is, whether it's the home wireless network or the access link that's causing the problem. You can think of multiple ways in which you can try to approach this problem. You could think about instrumenting end hosts, your servers, if you're an application provider, or clients inside the home network. But the problem there is that end hosts generally don't have sufficient visibility into the end-to-end path. So you don't have a global view, and although you can sort of identify the presence of a bottleneck, it's very difficult to identify the location because it's kind of difficult to infer properties of the network beyond a single hop or two. For example, even if you're on your laptop, you can't see traffic that goes to other devices inside your home network. Or if you're an application provider, it's difficult to know what's going on beyond your immediate network. So the gateway conveniently sits right between the two networks that we're interested in, the access link and the wireless link, and it has visibility into both these networks. Okay, so, how do we go about approaching this problem from the gateway? So there are two broad classes of techniques that you could use. You could use active measurements. And we know that the FCC has their Measuring Broadband America plan where they're running active measurements from home gateways. The problem there is that even though it gives us a lot of insight into the access link, these measurements don't really mean much per se for the user when they're struggling with a problem, an immediate problem. And because they're active measurements, they don't really represent the performance users see when they're running an application. And another problem is that most of us use the wireless network, and wireless conditions vary a lot. Even across a few seconds, you could have so much variation in a wireless network that an active measurement doesn't really give you much, even if you can run an active measurement on the wireless network. So we really need to be measuring passively so that any inference that we make actually represents user traffic and also end-to-end traffic. So, what metrics can we use from the gateway that can help us answer this question? So we use a very simple intuition based on how bottleneck buffers work. Well, the intuition is that packets get buffered at the bottleneck link. Well, here's a simple illustration of how a bottleneck link works. You have packets coming in from a non-bottleneck link at a rate faster than the bottleneck link can handle. And so the packets build up at the head of the bottleneck link. And there's another thing that happens in that the bottleneck link actually shapes traffic it gets more packets than it can handle, but it handles these packets at a very specific rate, which is its capacity. So there are two interesting things you can get out of this, depending on where you're observing the traffic from. Assuming that you're downstream of the bottleneck link, well, in our case, you're at the home, and the bottleneck link is the ISP's access link. So you see the packets that are shaped steadily. You see the shaped packets, and you actually see them in the form of steady packet arrivals. Supposing the bottleneck link were at the wireless network, that means that your vantage point has shifted, even though you're at the same point, the home wireless gateway. You're now at the head of the bottleneck link, and you can actually see the buffer building up, and you can actually see an increase in latency because of the buffer building up. So we actually use these two intuitions in order to make a detection. Let's go a little bit deeper into both of these. So here's an experiment under very controlled settings that actually shows the case where the access link is not the bottleneck. It's the wireless that's a bottleneck. So the x-axis shows time, and the y-axis shows instantaneous throughput at 10 millisecond intervals. And so this is an 802.11g network, so you can see that the throughput actually hovers around the 25 megabit per second mark. And what you can see here is TCP's congestion control at work. It's constantly trying to figure out the best rate at which to send. And there's a lot of variation, and this is what you would expect. Now, if you flip the network so that the access link is the bottleneck, and we can do that because we control it, change it to, say, 3 megabit per second and have the observation point the same, we see something entirely different. We see the shaped packets, and we see very little variation in the instantaneous throughput, right? That's because the bottleneck link has completely smoothed away any evidence of TCP's congestion control. And how do we, these are very two distinct properties, but, and we can actually measure these by looking at the coefficient of variation of packet interarrival times. The coefficient of variation is simply the standard deviation normalized by the mean. So in the first case, the CV parameter is about 0.88 in this example. And in the second case, it's about 0.05. So it's distinct enough that we can use this in order to detect whether a packet has passed, whether a flow has passed through a bottleneck link or not. So basically, the packets that arrive after a bottleneck link have really low coefficient of variation of packet interarrival times. Let's look at the second intuition. Here's a similar set of experiments, but over a much larger run, a few dozen runs. So here I'm showing on the x-axis achieved throughput over a similar network, and on the y-axis I'm showing the RTT over TCP, but between the gateway and the client inside the wireless network. So this is not the end-to-end RTT. Because we observe traffic at the gateway, we can actually split the RTT between the gateway and the client, and the gateway and the server. So this is the RTT inside the LAN network. So what we see here is what you would expect, that the TCP RTT, the average TCP RTT is about 5 milliseconds. It's slightly higher than you might normally expect. You would expect about 1 millisecond, but still within reason. But if you flip it and make the wireless the bottleneck, so basically remove the access link bottleneck, the picture changes again. So you see a very distinct property. The wireless RTT, the RTT over wireless has changed, has increased to about 25 to 30 milliseconds. So this is because of buffering inside the wireless gateway. And so again, we can use this very distinct property, the LAN RTT, in order to detect whether the wireless has bottlenecked the end-to-end flow or not. So we put these two properties together in order to build a very simple threshold-based algorithm that runs on the gateway. So we first collect packet traces, and we check to see if we have enough packets to even start making a decision. If there are not enough packets, there's no point in running this algorithm, so we just say, hey, there's not enough demand. If there are enough packets, then we compute the coefficient of variation of packet interarrival times, and then we check to see if it's if it falls below a threshold. If it does, then, well, the access link is the bottleneck. And if it doesn't, no, the access link is not the bottleneck. So we check to see what the LAN RTT is. And if it exceeds a threshold, then we say that the wireless link is the bottleneck. And if it doesn't, then we say that there is no last mile bottleneck. This is important because, well, you could have a sufficient flow rate, but you need not have a bottleneck in the last mile, and it happened due to multiple reasons. The end-to-end path could be too large, or there could be packet loss that TCP never really scales up to the rate of the bottleneck link, or the application demand doesn't really need TCP to scale up, or it could be too short. So there could be multiple reasons why there is no last mile bottleneck, even though there is traffic. So this is our technique. It's very simple. It's threshold based, and it actually it's lightweight enough to run on a home gateway. So we actually evaluated this in a control setting in a lab with using a lot of different types of access link throughputs, different wireless conditions, and we tested different thresholds with our devices, and we saw that we were able to get really high detection accuracy with simple thresholds, a CV parameter of 0.8 and a tau of 15 milliseconds. And in this case, let me clarify that the first threshold for coefficient of variation should work across any platform that you choose. But for the tau parameter, for the LAN RTT, it really depends on the hardware that you're using. So we used a Netgear Wonder 3800 home wireless router, and for that, the 15 millisecond threshold works really well. So we actually built a prototype system. It collects PCAPs on the device. It doesn't look into the payload at all. We don't care. We only look at the TCP IP headers, and even then, we don't really care what the actual addresses are. We just care about individual flows. So we completely anonymize all of these on the device using a per device, per run salt. And these gateways are really resource constrained. They only have a few megs of available storage and not a big CPU. So we only run this periodically for about 10 seconds at a time, or about 10,000 packets. And we also collect some meta information, like the number of devices using the wireless network, again anonymized, the wireless configuration, and so on and so forth. So we collect this data about 3 times an hour, and we do offline analysis of bottlenecks. So we actually deployed this in 2 different deployments. So the first pilot deployment was done on the Project Bismarck deployment, where we used the Netgear Wonder 3800 mostly device, a reasonable CPU, and a reasonable amount of storage to work with. And we deployed this in about 64 homes worldwide for about a period of 1 month. And more recently, we deployed this in the FCC SAMNOS in an MBA deployment, where they have a slightly weaker device, an older Netgear with a less powerful CPU and less storage, but we got way more footprint. We got about 2,600 homes in the US across 2 days. So let's look at some results. How frequent are throughput bottlenecks in the last mile? Well, this is a graph that shows, that splits the users that we had, the 2,600 users that we had, into bins according to the measured last mile downstream throughput. And this measurement, like I said earlier, is conducted independently by the FCC program. So what we see here is that, it's pretty consistent across different throughput bins. Users typically see about 40 to 55% of the time they see a significant throughput bottleneck. And it doesn't really change whether they have a really low access link throughput, although it's slightly higher for users in the less than 10 megabit per second range. And we don't really have too many users in the 70 to 80 bins, so we don't have any data for that. But it's pretty consistent between about 40 to 55%. Well, this conflates both the access link and the wireless link bottlenecks. So if you split them out, then we start seeing more interesting results. So this graph shows, when we detect a throughput bottleneck, we actually check to see whether it's an access link or a wireless bottleneck. And we see here that when users have throughput less than 10 megabits per second, access link bottlenecks dominate about 70-30 in terms of percentages. And that's not super surprising. You would assume that, you'd expect that when throughput is less, they're more likely to be bottlenecked by their access link rather than the wireless link. However, interestingly, as soon as throughput increases above about 20 megabits per second, users don't really get bottlenecked by their access link. It's more the wireless link that starts bottlenecking them. And it really dominates about 80-20 as soon as you exceed 20 megabits per second, which is surprising because most of these devices run 802.11n, and you'd expect that it supports at least 60-70 megabits per second as it's supposed to, right? I mean, it says 300, but over TCP, and if you assume all the problems that wireless networks come with, you'd get at least 50 to 60, not as low as 20 to 30. I mean, that's what you'd expect in an 802.11g network. So this is really surprising that we talk about the need to have faster broadband speeds, but users are having poor wireless networks in their homes. So one of the potential reasons why this could be the case is 2.4 gigahertz. We couldn't really validate this in the FCC deployment, but we were able to validate this in the pilot Bismarck deployment where we had both 2.4 and a 5 gigahertz radio on the same device. And we saw that devices that used 5 gigahertz consistently got higher throughput than devices that use 2.4 gigahertz. When we looked into the wireless frames, we also saw that the 5 gigahertz channel has consistently higher bit rates and also lower retransmission rates. And there could be multiple reasons why this could be the case. 2.4 gigahertz is typically more congested. It's also affected by non-802.11 devices like baby monitors or cordless phones. So the 5 gigahertz channel is cleaner. I don't know if it's systemic. I mean, if it starts getting more popular, you could start seeing more problems in 5 gigahertz as well. But right now, we see that the 5 gigahertz channel performs way better than the 2.4 gigahertz channel. Well, moving on. So what sort of throughputs do users get when their access link bottlenecked? So this result shows, well, when we detect an access link bottleneck, how does it compare to the capacity of that access link? And we know that, like I said, we have independent measurements of the capacity. It did not match what they're actually paying for, but we know from previous MBA reports that users, at least in the US, get really consistent performances from their ISP. So what we see here is when we detect an access link bottleneck, we normalize it by the capacity measurement from that user, and we see that users' throughput, the passive usage throughput actually matches very closely with the measured capacity. So this also independently sort of validates our algorithm. We can say that, hey, when we detect an access link bottleneck, this actually matches an independently measured active estimate of the capacity. But we also, have an independent validation of the previous reports that say that, yes, users are getting pretty consistent performances from the user without going into whether it actually meets their advertised rates. And when users are not access link bottlenecked, we see that their throughput is way less than the measured capacity. So the status. So we have a proof of concept system that works on OpenWRT, which we deployed in the pilot deployment, and also a version that we deployed on the FCC platform. And we're still actively deploying this for increased robustness. Although this was more of a sampling proof of concept system, we also have an online version that we demoed at SIGCOMM last year. And this algorithm has significant caveats. It doesn't really work for upstream traffic. We can only detect bottlenecks for downstream traffic. But I guess it's not a huge problem because rates are not symmetric, at least now. And it doesn't really work when the upstream is a wireless network, like a 4G or a WiMAX network, because the technique depends on a property of queues that make it work conserving. We are, however, looking for further larger deployments in home routers. So if you're interested in deploying this tool, please let us know. So in conclusion, I presented home or access, which is a lightweight and accurate system to locate last mile downstream throughput bottlenecks. We deployed this in 2 largest deployments in resource constrained gateways. So yes, this actually works even in home gateways. And we're looking for further deployments. And we actually had some really interesting results, which we are still digging into. At least initially, we see that access link bottlenecks are only common when throughput is less than about 20 megabits per second. And beyond that, it's pretty much almost always the wireless that bottlenecks performance. Please, contact me if you're interested in the tool, if you're interested in deploying it, if you'd like a demo. And I'm happy to take questions now.
Morning. My name is Joel. I work for Wikipedia. I'm wondering if you tried to correlate client signal strength and maybe throw out clients that had very poor signal strength while they're on the Wi-Fi. Everybody roams out of their good Wi-Fi range, and obviously you'll have a lot less performance in that condition.
So we don't get any wireless metrics in the FCC deployment, but we do have signal strength in the smaller pilot deployment. Well, you could deal with it 2 ways. Yes, you could throw out users that have low signal strength, but the fact that they're trying to use the network when they have low signal strength means that they're trying to get something out of it, right? So we should be able to see that they are being bottlenecked by the wireless, and the users may not know that they have low signal strength.
I guess my point was that you're going to have, at least my house, I have a lot of different devices, and they're all connected and have very variable quality of signal strength.
Hello, my name is John Brzezowski from Comcast. So it seems like you've got a pretty good way to determine if you've got media issues in the home from client to a router and then from the router to the network. So I'll kind of defer my question maybe for later on that front. Question I have for you is, do you factor in V4 versus V6 into your methodology, and do you factor in the presence of a carrier grade NAT inside of your network as well, or as part of this methodology?
So our technique shouldn't be affected by either of those, because we really depend on TCP and the way TCP works in order to make the decision, and that should be independent of either of those.
Okay, thanks.
Phil Rosenthal from IS Prime. I'm curious if you, so you had it in, I guess, a number of different ISPs, and but with only a limited number of Wi-Fi access points. It's certainly possible that different ISPs and different model access points might have different size buffers, different queue management. Some might be running red, some tail drop. Have you considered how that falls into your methodology?
So we tested it on not too many access points. We only tested it on the access points that we had a chance of deploying on. So yes, you're right. We need to calibrate this whenever we have a different deployment. One half of the algorithm needs to be recalibrated, which is the latency threshold that we use to say that the wireless is a bottleneck. And it is entirely possible that depending on the queuing technique that you use inside the wireless access point, the results may vary, your mileage may vary. I mean, if it's a very efficient queuing algorithm, it's possible that there's overlap between the medium access time and the queuing delays, and that might start confounding us. But as long as, for the other half, detecting an access link bottleneck, it should be really independent of that, because as long as the queue is work conserving, it should give us this neat little distinction between a bottleneck link and a non-bottleneck link.
Thank you.
Hey, I'm Akhil Karmalkar from Microsoft. Actually, I had almost similar question as him about the thresholds which you guys are using. So, are you using any machine learning techniques to for the variable thresholds? Do you change it dynamically according to congestion in the network, or?
Well, we are trying to detect congestion in the network. We did try fancy things. I mean, we saw that a simple static threshold just works perfectly fine. So we really didn't need to.
So that means you keep the same threshold all the time?
For a particular platform, yes.
Okay.
Okay, just a program note. I think we've got a number of questioners here, so we'll close the question queues now and thanks. I mean, no. I mean, answer the questions who are queued now. Newcomers, we can't service anymore at the queues.
Adrian Chad Norse. So one of my many hats is making wireless stuff less terrible. A couple of questions. Firstly, did you test the behavior of commercial access points for office and enterprise deployments versus home deployments? And I ask because having worked on rate control, I know that like OpenWRT and the consumer access points, their rate control focuses on throughput, not latency and fairness versus, well, anything you buy over $500.
We didn't.
Okay.
Because all the deployments were, home commodity routers, so that's what we tested on.
It doesn't surprise me because all of those are tested for throughput.
Yes, and that's something that we have seen typically across both modems and wireless routers in the home space.
Well, having worked at Atheros for a little bit, everything that has the Atheros chip tends to have the same rate control, and so you end up with this wide body of equipment that has the same vendor code that behaves precisely the same way. So, okay. The second question was, were you looking at aggregation efficiency in 11N? Because for flows under about 20-25 megabits, you'll probably find that aggregation isn't kicking in and it is actually sending one packet at a time without aggregation. And then as you go over 20-25 megabits and it starts aggregating, you hit this, the air gets full, but you get more efficiency out of it.
So I don't understand 802.11n very deeply, but we did run a lot of empirical measurements at different access link throughputs, like different up, 10, 20, up to 80 megabits per second. And we did see that as long as we are able to achieve either the access link, whatever we set it to, or what we expect the wireless link to be, then these thresholds work really well, even if there is aggregation. So, if you think about it, 15 milliseconds is a pretty large threshold. We did consider different problems with medium access, contention, distance, retransmissions, and even accounting for all of that, you should still see a clear gap between the case where there's a wireless bottleneck and when there isn't.
Cool. Thank you.
Back there.
Janai Yangar, Google. Thanks very much for bringing this here. This is, the insights are very nifty. And they're being used quite nicely. That's what I was thinking about, the primary thing that gives you the ability to figure out whether the bottleneck is upstream or not. And that is TCP's probing and trying to figure out what the right rate is. And as I think about that further, I was wondering how something like this would play with other TCP congestion control mechanisms that don't do the kind of rate probing that you have here. And just to finish my question, I imagine that there's a lot more of that kind of variation going on in the UDP world. So my question to you is, have you seen data about how this plays when you're looking at UDP flows, which have a much wider variation of behaviors?
Well, I mean, this would obviously break down if it's a CBR UDP flow, right? Because you really can't make out, unless you know at which rate it's being sent at, you can't figure out, whether it's been shaped or not. As far as TCP goes, as long as there's some probing of the network, that would introduce some variation, which the bottleneck link would then smooth out. So we should be able to detect that.
I'd imagine the same thing is true for UDP, because most flows are not CBR.
Yep.
They're doing
if it's not CBR, yes, we can totally apply this.
Have you looked at UDP flows?
We didn't, because most application traffic is TCP. But we could focus on specific applications, I suppose.
Thank you.
Either one. All right then.
Spencer Dawkins from Huawei. This is very interesting. I'm actually probably standing up here because I'm Transport Area Director at the IETF. It's very interesting work. Thank you for doing it, and thank you for bringing it out where people can look at it.
Yep.
You don't have to worry about what I'm about to say for a year or two probably, but the work that people are doing to reduce buffer bloat, and especially work that we're trying to do with delay-based congestion mechanisms, detection mechanisms, rather than loss-based detection mechanisms. That may have some interesting interactions as you continue this work. That'd be really interested in seeing how that shakes out. But again, thank you for doing it.
Well, it's an interesting point because it's something that I've been considering, because if you think about it, what the wireless part of it actually depends on is an excessive, maybe, buffer, right? So if you fix that, then the question is whether the increase in latency that you see with medium access or contention, that sort of thing starts infringing on a bottlenecked, a purely bottlenecked wireless link. The answer is I don't know. But yes, that is definitely something to consider. I mean, it raises, the earlier point that someone else said, it's optimized for throughput rather than latency, right? So once you remove that optimization, all bets are off. But we started this work thinking about different metrics, like trying to correlate the bit rate, retransmission rate, and that sort of thing. So maybe those sort of metrics would start becoming more interesting.
Thank you.
Thank you.
And last.
Yes. Given your research on wireless bottlenecks, what role, if any, do you see as femtocell and related technologies for mitigating wireless bottlenecks?
Well, femtocells basically make, it's for improving your cellular connectivity, right? It should be independent of bottlenecks inside your home. There's still that one hop inside the home that femtocell doesn't really solve, right?
Okay.
Unless I'm misunderstanding your question.
Well, I think you've answered it.
Okay. All right.
Okay. Thanks very much.
Thank you.